show you incredible things. Magic, madness, heaven, sin. Saw you there and I thought, oh my God, look at that face. You look like my next mistake. Love's a game, wanna play.
Good morning, good afternoon, good evening, whatever the case may be, we are back and better than ever. And do you ever feel that there is a blank space in your life? Well, ladies and gentlemen, I'm here to tell you when you have that feeling, mathematics can not feel. You can feel the mathematics, but mathematics will fill that blank space. We are talking about planes. This is going to be a 2, maybe 3-part discussion. This is part 1. Have some awesome planes here for you to take a look at. See you again. All right. All right, giddy up. So, if we were to reach the point with coordinates PQ from the origin, okay, we would move P units in the x direction and Q units in the y direction. We all know that. No big whoop, right? Okay. So let's consider the point 3, 2. So 3, 2, there she is. Okay. And now let's consider the unit vector I, right there, there's I, and the unit vector j. Yes? Right there. Okay. And to get to P, this point P, I could do it with vectors by going, okay, so 3i, right, the vector 3i, and then plus 2j, yes, that ends up giving me the most awesome vector right here, 3i plus 2j, right? Let's see if I get the arrow right. Not bad for the first try. So this is the vector 3i plus 2j, yes? But that's not the only way that we can accomplish this, okay? Let's say that we go to 3, 2 again. It's right here, same spot, yes? But our unit vectors, or one of our unit vectors, it could be both of them, but just for simplicity, we'll do just one differently. Let's say I still have the unit vector I, yes, right here, okay? It has a magnitude of 1, and I have this vector j, yes, okay, that's this many units long, okay, and it may or may not be 1. Actually, it wouldn't be 1. We know it's not 1, but I is still the unit vector. Well, to get there, to get to the point 3, 2, couldn't I do this vector, and then go up here to this vector, right? And then, wouldn't that be the, oh, sorry about that arrow. Wouldn't this right here be the vector 2i, as defined from here to here is I, and from here to here is j, so this would be 2j, right? So the same vector could be defined if I start with these basic vectors as, let me draw the vector here, right there, okay. This could be defined as 2i plus 2j, okay. It just depends on the original vectors and what multiple we can use. But the result is the same just because I started out with 2 different vectors, okay. So the moral of this story is we can see that any point in the plane can be reached by going a certain number of units in the direction of those vectors. And it can be a multiple of those units, okay? So if I have 2 vectors, let's say d1 and d sub 2, I don't know why I put a dot there, then I can get there by some multiple. I can get to any point on the plane as a multiple d1 lambda plus mu d sub 2, okay? No big whoop there, right? Okay, and in this case, lambda would be 2 and mu would be 2. So not a big deal at all, okay? So let's take this to 3 dimensions, okay? Now let's consider a plane that does not pass through the origin, Okay, so thanks, Ruby. We have this plane here, this orange plane right here. See it? Yes. And to reach a point, oops, sorry about that. To reach a point in the plane, starting from the origin, we go to some other point in the plane first. So we start at the origin here, right? And then we zoom up and we hit this random point on the plane, okay? And then we move along two directions which lie in the plane, okay? So here and then here. And this means that every point in the plane has a position vector of the form A, this vector A, plus lambda d1 plus mu d2. And A is a position vector of one point in the plane. And remember, a position vector is just, if I know these coordinates are like, I don't know, 1, 2, 3, then it is the vector 1, 2, 3, because it's just from the origin, right? Sorry about the messiness of the 3. I'm using my mouse here, not the pen. That's a horrible 3. I'm so sorry about that. Okay. And then, so we have the position vector, and then d1 and d2 are two vectors parallel to the plane, but not parallel to each other. By the way, vectors that are parallel to the plane are defined to be in the plane. Any two vectors in the plane, okay, are parallel to each other, or are parallel vectors, okay, but they don't have to be parallel to each other. Let me rephrase that. I said they're parallel vectors. They're parallel to the plane, okay? If two vectors lie in the same plane, then they are parallel to the plane. All right, d1 and d2 do not need to be perpendicular to each other. So we can lambda them and mu them and get to whatever point we want to. That's the whole moral of the story. Well, why do we care about that? Well, that leads to an equation, a vector equation of a plane. The plane containing point A and parallel to the directions of vectors d1 and d2 has a vector equation r equals a plus lambda d1 plus mu d2. I am so popular today. Okay. That is a general form of a vector equation. And what this allows us to do is it represents every single point on the plane, because I can get to every single point on the plane using this equation. And here I have, from our formula sheet, I used a text that had different nomenclature here. On your formula sheet, it's just r equals a, that's the same. And instead of d1 and d2, they use vectors b and c. But lambda and mu are universal generally. And we'll get to this in a second here, down here. Okay, so that's easy peasy. All right. So now, alternatively, if two non-parallel vectors b and c are parallel to the plane, that means the vectors lie within the plane, then the normal vector n equals b cross c, the cross product of these two vectors, remember that, is perpendicular to any vector or line in or parallel to the plane. Okay, so here's a nice illustration of that. Okay, so let's suppose we have a point r, x, y, z. It's right here, and it lies on the plane containing a known point. So we know the coordinates of this, and then this is any point. R is any point, A is a known point. And then we have a normal vector, n equals ABC, normal to the plane. Okay. Now, AR is perpendicular to n. Any vector in this plane is going to be perpendicular to the normal vector. That's the definition of a normal vector. It's perpendicular to the plane, so it's going to be perpendicular to any vector that is in the plane. Well, if that's true, then the dot product of the normal vector and any vector in the plane has to be 0. So if we put the components of those, the vector ABC dot, and what is vector AR? Well, it's x minus x1, y minus y1, z minus z1. That's equal to 0. So we figure out that dot product, do a little bit of algebraic manipulation here, and lo and behold, we have a vector equation in Cartesian form of the plane. Why is it Cartesian? Well, remember, we know these, yes? This is a known point, like 2, 3, 4, or whatever. And if we know that, and we know the components of the normal vector, which we must, then we're going to be able to add these together and get a constant. And x, y, and z here represent any point on the plane. Any point on the plane. Okay? So that leads to n dot ar equals 0 as another form of the vector equation of the plane. It could also be written as n dot r minus a, representing all the points here minus all the points here to get the components. Or r dot n equals a dot n, just with some algebra. Okay, but here's the biggie. If a plane has a normal vector n equal to abc and passes through some known point, then it has the equation that we just derived here. This is the Cartesian equation of a plane. Okay, and so there we go. I've shown you, I've derived your vector equation of a plane, the equation of a plane using the normal vector here, and the Cartesian equation of a plane. Okay, and these are all on your formula sheet. So that's a lot of talking, no action. I am going to stop. We're going back to T Swift to take us out here, and we will pick it up in planes part 2. It's going to be forever, boys and girls. It will not go down in flames. Don't tell me when it's over. I am... Oh!